Module 4B, Acoustic Design for Studios. At the completion of this module, you will understand the 4 considerations that affect room acoustics: sound isolation, the dimensions of the room shape, and the qualities of the surfaces within the room, known as room acoustics. By far the most important consideration of room acoustics is dealing with noise. We define noise as any unwanted sound. Now, noise is everywhere. We can't get rid of it, but we can reduce the effects of the noise to a point where it's no longer bothersome. And what is that point? How much noise is too much noise? Well, it depends on the use of the room. So, in order to be able to measure the noise, acousticians developed noise criteria so they can measure the background levels of a room. This graph shows noise on the left, measured in dB of sound pressure level. Shown on the graph itself are various noise criteria, all the way from 70, which is a very noisy environment, down to a noise criteria of 20, which is very quiet. Notice that the noise criteria changes with frequency, shown along the bottom. Applying these noise criteria to various rooms, we get an idea of how much noise is tolerable. For critical situations such as broadcast and recording studios, noise criteria needs to be very low, less than 20 dB. In less demanding situations, noise levels can be higher, 20 to 30 dB, and classrooms are ideally designed to have a noise criteria between 30 and 35. In order to assure that the room meets the proper noise criteria, the room must be isolated to keep sound from leaking in and to keep sound from leaking out. Here we introduce another factor known as the sound transmission class, which will allow us to determine how much we need to block the sound in order to meet the necessary noise criteria. For example, if we are designing a room that we want to use for recording, where we want a noise criteria of 20, and we measure the outside noise and we find that it's on average 80 decibels of sound pressure level, to calculate the sound transmission class for the room that we'll need to build, we start with the 80 decibels of the sound from the outside and subtract the 20 decibels of the noise criteria that we need to wind up with, and that tells us that we need a sound transmission class of 60 decibels. Those are pretty hefty walls. And perhaps even more important is the amount of sound that leaks out of the room. If our musicians play at 110 decibels, and we've built a room with a sound transmission class of 60, the amount of sound leaking out is going to be 110 minus 60, or 50 decibels of sound pressure level. This may be way too loud for the neighbors. Well, once we've designed our room that's going to be quiet enough in either direction, our next consideration is the overall dimensions of the room. That would be height, width, and length. These dimensions determine the sound of the room. Recalling that every frequency has a wavelength, those frequencies whose wavelength is equal to one of the dimensions of the room will tend to resonate in the room. Much like blowing air into an empty bottle, the bottle resonates at certain frequencies, depending on the size of the bottle. And if the room dimensions happen to be even multiples of each other, we can get a buildup of these resonant frequencies, which creates a very unnatural sound. For example, the frequency of 100 Hz would have a wavelength which is equal to 1130 feet per second, the speed of sound, divided by the frequency, or the wavelength for 100 Hz would be 11.3 feet. If the dimensions of the room happen to be a height of 11 feet, a width of twice that, or 22 feet, and a length of 3 times that, or 33 feet, we would get a tremendous buildup of 100 Hz within that room, and sound recorded in that room would sound pretty muddy. The shape of the room also has a contributing factor to how the room sounds. Parallel surfaces tend to build up resonances at certain frequencies. To minimize this, walls are often made non-parallel, or splayed. Finally, the treatment of the room itself has a lot to do with the room acoustics, or how a room sounds. When sound hits a surface, one of 5 things will happen. The sound could be absorbed, or it could be reflected, or it could be a combination partially absorbed and partially reflected, or the sound could be diffracted, or the sound could be diffused. All material has the ability to absorb some sound as determined by its noise reduction coefficient. Hard painted surfaces that are very reflective will have a very small noise reduction coefficient. At the other extreme, materials that are soft or porous are likely to have a high noise reduction coefficient. This noise reduction coefficient varies between 0, which means the material absorbs just about none of the sound, and the number 1, which means that the material absorbs all the sound. This noise reduction coefficient will vary with the frequency. For example, ceiling tiles will absorb just about every frequency above 2000 Hz, but practically nothing below 100 Hz. Diffraction occurs when sound bends around a surface. And diffusion is the tendency for sound waves to spread as they bounce off of surfaces. This is a highly desirable aspect of a studio, as it spreads and evens the sound throughout. This concludes Module 4, Acoustics and Psychoacoustics.